The Burj Khalifa building, which stands firmly on loose sandy soil, braving the strong Arabian winds, is genuinely a modern engineering marvel. In this video, we will explore all the design secrets of the world's tallest building, starting from its surprisingly simple hexagonal core. This incredible feat of civil engineering can even confuse the wind due to its unique shape and lightning with the help of modern technology. Let's get into it. Hexagonal core. The soul of the Burj Khalifa is its hexagonal core. This RCC-built core is the ultimate hero, enabling the Burj Khalifa to keep standing despite the devastating windstorms of Dubai and helping keep the weight of the building balanced. The hub also accommodates the entire lift system of this building. A slender core is volatile in theory. It could fall at any time, but Skidmore, Owings & Merrill, SOM, the company that designed Burj Khalifa, came up with an innovative solution. They took inspiration from the buttresses we usually see on dams to hold the core of the wall and used similar supports around the body to make the towers around the buttresses practical. They infused a step-shaped design to the buttresses. We know buildings are always vertical. They are always right. Buttresses. Here is the main twist. Skidmore engineers designed the buttresses so that you can live next to them without even realizing it. They are buttresses. The architects of the Burj Khalifa also efficiently used this space for corridors, so from the lift, people walk to their flats between the buttress walls. The architects then designed massive glass facades around the buttresses, giving all the hotels and living spaces inside the fronts a breathtaking view from all sides. The support needed for these glass facades came from these crosswalks and columns. The primary function of the crosswall is not to support the shows. To understand it, let's check out an example. There's a sandstorm in Dubai, but no crosswalks. The forces of resistance coming from the buttresses on the opposite side save the building from toppling over on the left-hand side. The power of the wind is resisted by the combined effect of both these buttresses, which are at an angle. However, such a slender building and a massive force from the heavy sandstorm will lead to the whole building structure bending too much. We must understand the notorious property of concrete and its weakness against tensile stress. When a concrete block turns, tensile stress is caused in that section of the block. Concrete can only withstand a small amount of tensile stress, and it will form cracks quickly if the tensile stress continues. That's why the hexagonal core has steel bars inside it. The steel bars absorb most of the tensile stress. However, if the body bends too much, the concrete section of the body won't be able to deal with the tensile stress. The best method to prevent a cantilever beam from bending in structural engineering is by using an I-shaped section. That's precisely what we do when we connect the cross walls to the buttresses. If you observe, you can see the shape has now become like an I cross-section. The building is structurally strong and can withstand tensile stress without bending. Mechanical floors. Can you see the black stripes on the original Burj Khalifa design? They represent the mechanical floors. To understand their importance, take a look at this diagram, which shows all the columns used in the Burj Khalifa. It's a complex jungle. These columns are stable when they're connected to the floors. The foundations are already strong since they're connected to the core. The mechanical roofs house electrical, air refrigeration systems, and water tanks that bring the Burj Khalifa to life. Nobody stays on those roofs. These floors have a different appearance because they're covered with concrete walls and pipes. Workers use them to grip when cleaning the glass facade. Steel superstructure. The exciting thing is that the concrete core supports only about 70% of the Burj Khalifa. The top 25% doesn't have any core support. It's a steel structure, although the Burj Khalifa mainly resists bending. The top of this superstructure can bend and sway by about 6 feet in windy storms. Since steel can easily withstand tensile loads, if you experience an oscillation like an earthquake, don't panic. It's probably the Burj Khalifa swiftly saying hello to the winds. Thanks to the reinforced concrete, the hexagonal core can withstand torsion, which is the twist and shear stress caused by the wind. This excellent buttressed core system is why the Burj Khalifa is also known as a stiffened rod in the face of the wind. Vortex shedding. Our design approach has resulted in a Burj Khalifa that looks like this. However, the real Burj Khalifa looks like this, an asymmetrical structure instead of a symmetrical one. Why did the designers of this marvelous structure go for the asymmetrical design? When the wind passes around a structure, it can lead to a beautiful and dangerous fluid mechanics phenomenon called vortex shedding. The vortices dance looks interesting, but it's difficult to manage because these vortices fluctuate, generating a fluctuating force on the building. If the natural frequency of vibration of this building is the same as the frequency of these fluctuations in power, the building will violently oscillate like this, a phenomenon called resonance. These oscillations will keep increasing and could eventually make the Burj Khalifa fail. Spiral. To overcome this issue, someone who designed the Burj Khalifa came up with an architectural innovation. Bill Baker and his team's idea to break the vortex shedding was to create a spiral in the Burj Khalifa. A spiral shape is the best solution to kill vortex shedding as it confuses the wind when the body varies. Can you find a hidden spiral in this building structure to discover the remote coil in Burj Khalifa? Consider these simple towers with varying heights but many petals. You can see the circle. Now, if you observe the Burj Khalifa, you can see it has also been constructed using the same technique, towers of varying heights forming a discrete spiral. Bill Baker used one more spiral version for the top of the Burj Khalifa. He specified varying angles for the tiers at this height. This dense spiral helps to fight against tip vortex shedding. These innovations are why the Burj Khalifa has successfully reached 830 meters, even though initially it was only designed to reach 518 meters. An additional 312 meters, almost as tall as the Eiffel Tower, was added during construction. What a marvelous achievement for Dubai! But how is such a heavy structure able to stand on the loose sandy soil of Arabia without sinking? The engineers of this building couldn't find any hard strata in this area even after going 140 meters down. These sedimentary rocks are also less intense, so the engineers faced two challenges: the ground's poor load-bearing capacity and the structure's differential settlement. To tackle these problems, they used a raft attached to the hexagonal core eye sections and columns. The raft was made of a slab of thick, high-performance RCC structure. This raft distributes the weight of the building onto a larger area of sand equally and thus resists differential settlement. However, how will the soft sand and rocks bear such a vast mass? This raft will sink. Bill Baker came up with a solution using multiple RCC piles. The friction between the surface of these piles and the weak but stiff sedimentary rocks will resist the load of the building. Did you notice the beautiful flower-like petals just above the foundation of the building? This structural design, especially these petals, was inspired by one of Dubai's most widely cultivated flowers, the spider lily. Lightning arrestor. These lightning strikes on the Burj Khalifa are fascinating but alarming. At the very top of this building, a small peculiar device keeps the Burj Khalifa from burning up, the lightning arrestor. The dome is connected to sensor equipment, which is connected by a tiny battery. As soon as the arrestor detects a supercharged cloud nearby, it immediately generates opposite charges on its surface to attract the lightning towards it. The electron flow of the lightning is then passed through the outer column steel structure and dissipated into the earth pits via the steel inside the foundation piles. The electrons travel only through the external columns due to the skin effect. Lifting the concrete, Burj Khalifa is Dubai's lightning rod. Its lightning arrestor collects the lightning strikes of almost the entire Dubai. Thanks to its excellent height, the most exciting part is how they lift the concrete to this height despite Dubai's warm weather. Even if they had used the most powerful pumps, the concrete would have solidified before reaching the destination. Instead, the team used a particular grade of concrete named C50 and C80 mixed with ice as they pumped it up. This work of pouring the concrete into molds was done at night and would immediately be set. The team completed one floor every week. The entire project took 6 years to complete. You may be thinking, is it possible for another building to overtake the height of the Burj Khalifa as the building gets taller? The design challenges we saw in this video also increase. If the engineers are smart enough to overcome these challenges, they can achieve an even taller building. It's no easy task, though. Now that you have understood the great details that keep this megastructure, the Burj Khalifa, standing tall, let's take a tour inside this building. Very soon, we will reach the top of the Burj Khalifa and the end of this video.